In this video and the next, we're going to take it to the next level and peer under the hood into implementations of balanced binary search trees. Now, frankly, the nitty-gritty details of all balanced binary search tree implementations get pretty complicated. And if you really want to understand them at a fine-grained level, there is no substitute for reading an advanced algorithms textbook that includes coverage of the topic and or studying open source implementations of these data structures. I don't see the point of regurgitating all of those details for you here. What I do see the point in doing is giving you the gist of some of the key ideas in these implementations. In this first video, I want to focus on a key primitive, that of rotations, which is common to all balanced binary search tree implementations, whether it's red-black trees, AVL trees, B or B plus trees, whatever, all of them use rotations. In the next video, we'll talk a little bit more about the details of red-black trees in particular. So what is the point behind these magical rotation operations? Well, the goal is to do just constant work, just rewire a few pointers, and yet locally rebalance a search tree without violating the search tree property. So there are two flavors of rotations, left rotations and right rotations. In either case, when you invoke a rotation, it's on a parent-child pair in a search tree. If it's a right child of the parent, then you use a left rotation. We'll discuss that on this slide. And a right rotation is in some sense an inverse operation, which you use when you have a left child of the parent. So what's the generic picture look like when you have a node X in a search tree and it has some right child Y? Well, X in general might have some parent. X might also have some left subtree. Let's call that left subtree of X capital A. It could, of course, be empty. And then Y has its two subtrees. Let's call the left subtree of Y B and the right subtree C. It's going to be very important that rotations preserve the search tree property. So to see why that's true, let's just be clear on exactly which elements are bigger than which other elements in this picture. So first of all, Y being a right child of X, Y is going to be bigger than X. Now, all of the keys which lie in the subtree A, because they're to the left of X, these keys are going to be even smaller than X. By the same token, anything in the subtree capital C, that's to the right of Y, so all that stuff is going to be even bigger than Y. What about subtree capital B? What about the nodes in there? Well, on the one hand, all of these are in X's right subtree, right? To get to any node in B, you go through X and then you follow the right child to Y. So that means everything in B is bigger than X. Yet, at the same time, it's all in the left subtree of Y. So these are all things smaller than Y. Summarizing, all of the nodes in B have keys strictly in between X and Y. So now that we're clear on how all of the search keys in the different parts of this picture relate to each other, I can describe the point of a left rotation. Fundamentally, the goal is to invert the relationship between the nodes X and Y. Currently, X is the parent and Y is the child. We want to rewire a few pointers so that Y is now the parent and X is the child. Now, what's cool is, given that that is our goal, there's pretty much a unique way to put all of these pieces back together to accomplish it. So let's just follow our nose. So remember the goal. Y should be the parent and X should be the child. Well, X is less than Y, and there's nothing we can do about that. So if X is going to be a child of Y, it's got to be the left child. So your first question might be, well, what happened to X's parent? So X used to have some parent, let's call it P. And now X's new parent is Y. Similarly, Y used to have a parent X, and there's a question, what should Y's new parent be? Well, Y is just going to inherit X's old parent, P. So this change has no bearing for the search tree property. Either this collection of nodes was P's left subtree, in that case all of these nodes were less than P, or this subtree was P's right subtree, in which case all of these are bigger than P, but P could really care less which of X or Y is its direct descendant. Now let's move on to thinking about what we should do with the subtrees A, B, and C. So we have 3 subtrees we need to reassemble into this picture, and fortunately we have 3 slots available. X has both of its child pointers available, and Y has its right child available. So what can we put where? Well, A is the subtree of stuff which is less than both X and Y, so that should sensibly be X's left child. That's exactly as it was before. By the same token, capital C is the stuff bigger than both X and Y, so that should be Y, the bigger node's right child, just as before. And what's more interesting is what happens to subtree capital B. So B used to be Y's left child, but that can't happen anymore because now X is Y's left child. So the only hope is to slot capital B into the only space we have for it, X's right child. Fortunately for us, this actually works. Slotting B into the only open space we have for it, X's right child, does indeed preserve the search tree property. Recall we noticed that every key in capital B is strictly between X and Y, therefore it better be in X's right subtree and it better be in Y's left subtree, but it is. That's exactly where we put it. So that's a left rotation, but if you understand a left rotation, then you understand a right rotation as well, because a right rotation is just the inverse operation. So that's when you take a parent-child pair, where the child is the left child of the parent, and now you again want to invert their relationship. You want to make the old child the new parent, and the old parent the new child. And once again, given this goal, there's really a unique way to reassemble the components of this picture so that the goal is accomplished, so that Y is now the parent of X. So what are the laudable properties of rotations? Well, first of all, I hope it's clear that they can be implemented in constant time. All you are doing are rewiring a constant number of pointers. Furthermore, as we've discussed, they preserve the search tree property. So these nice properties are what make rotations the ubiquitous primitive, common to all balanced search tree implementations. So this, of course, is not the whole story. In a complete specification of a balanced search tree implementation, you have to say exactly when and how you deploy these rotations. You'll get a small taste of that in the next video, but if you really want to understand it in more depth, I again encourage you to check out either a comprehensive data structures textbook, check out a number of balanced search tree demonstrations, which are readily available on the web, or have a peek at an open source implementation of one of these data structures.